This method can help to understand key subjects in the field of additive manufacturing, such as resin formulation and post-printing treatment.
The main advantage of this technique is that it enables the accurate and on-demand fabrication of sustainable products.
This method will provide insight into laser-based stereolithography, but it can also be applied to other 3D printing techniques, such as digital light processing.
To begin, pour 50 grams of 110 decanediol diacrylate in a 500 milliliter Erlenmeyer flask. Add 1.0 grams of TPO and 0.40 grams of BBOT to the flask. Equip the Erlenmeyer flask with a mechanical stirrer and stir the mixture at 200 RPM for 5 minutes at room temperature in order to dissolve the TPO and BBOT in the acrylate monomer. Add 100 grams of penta-erythritol tetraacrylate and 100 grams of multifunctional epoxy acrylate to the mixture. Now stir the mixture at 200 RPM for 30 minutes at 50 degrees Celsius to ensure a homogeneous resin. Remove the mechanical stirrer and fit the flask with a stopper. Wrap the flask in aluminum foil to protect the bio-based acrylate photopolymer resin from light. Now cover the bottom plate of a rheometer, characterized by parallel plate geometry, with the photoresin. Set the gap between the plates at 1 mm and cover the rheometer with a UV-resistant hood. Measure the resin viscosity at room temperature at shear rates from 0.1 to 100 inverse seconds. Turn on the SLA 3D printer and select the Open mode.
Depending on the architecture of the product, a support structure can be integrated in the 3D model to stabilize the construct during fabrication.
Start the model preparation software on a computer. To choose the desired print settings, select Clear for material, version V4, and 50 micron layer thickness. Open the digital model of the complex-shaped prototype, which is a standard tessellation language file. Then choose the location and orientation on the build platform. Upload the print job to the SLA 3D printer. Now pour 200 milliliters of the bio-based photoresin into a resin tank. Open the 3D printer and mount the resin tank properly. Mount the build platform and close the 3D printer. Following preparation of the 3D printer, start the print job. Allow the 3D printer to fabricate complex-shaped prototypes. Do not open the printer until the print job is finished. For the demonstrated protocol, the wavelength of the UV laser is 405 nanometers. The print time of the object is 2.5 hours and is shown here in fast motion. When the print job is finished, open the printer. Remove the build platform with the produced parts attached and close the printer. Open the washing station filled with isopropyl alcohol and insert the build platform. Start the procedure and rinse for 20 minutes to remove any unreacted resin. When the rinsing procedure is finished, remove the build platform from the washing station and detach the prototypes from the build platform. Allow the prototypes to air dry for 30 minutes. In the meantime, preheat the UV oven at 60 degrees Celsius. Open the UV oven and quickly place the prototypes on the rotating platform. close the UV oven and cure for 60 minutes at 60 degrees Celsius to ensure complete conversion. When the post-curing procedure is finished, open the UV oven and take out the prototypes. To characterize the surface morphology of complex-shaped prototypes, cut approximately 1 centimeter of internal helix from the complex-shaped prototype using a razor blade. Attach the sample to the sample holder with double-sided carbon conductive tape. Prior to imaging, coat the sample with 30 nanometers of platinum palladium on a sputtering system. Now insert the sample into a scanning electron microscope operating at an accelerating voltage of 5 kilovolts. Acquire several images of the sample at 30x and 120x magnification. The viscosity of the renewable resin is an essential parameter in the 3D printing process and is controlled by the monomer to oligomer ratio. Typically, a shear rate of 100 inverse seconds is achieved during the recoat of liquid resin in the printing process. All bioresins have a viscosity below 5 Pascal seconds and are appropriate for application in stereolithographic printing equipment. Shown here are representative results for the mechanical behavior of the objects printed from various bioresins, including tensile strength and E-modulus. However, optimization of the post-printing treatment by varying the duration of washing, drying, curing, and temperature of curing can lead to a significant improvement in mechanical performance. The smooth surface and high feature resolution of the complex-shaped prototypes is revealed by the electron microscope. The serrated vertical edges of the helices arise from the layer-by-layer SLA printing process, in which the top of an exposed layer receives a larger UV dose compared to the back of a layer. The extent of surface cracking is related to the initial resin viscosity.
After its development, this technique paved the way for application of cost-competitive bioresins to facilitate waste-free and local manufacturing of sustainable products.
Don't forget that working with acrylates can be hazardous. Precautions such as wearing safety glasses and gloves should always be taken while performing this procedure.